So this time we're gonna solve an example that involves an unsteady flow device. Let's read the problem statement together and sketch our system. There is a rigid tank. And it has a volume of 0.3 meter cube. So since it says rigid tank, no matter how many energy interactions gonna take place, the volume of the tank doesn't change. So it is filled with saturated liquid water. We identify our system as water, and it is at 200 degrees Celsius. There is a valve at the bottom of the tank. Okay. Of course, we need to define our control volume, which is our system, by defining our boundaries. That's what we did. And a valve is opened at the bottom of the tank and a liquid is withdrawn from the tank. Heat is transferred to the water such that the temperature in the tank remains constant. Okay, so heat is getting in to the system such that the temperature stays constant. So at the state 1 and the second state, our temperature is the same, and this is achieved by the heat transfer that is getting in. Now the question asks, determine the amount of heat that must be transferred by the time 1/2 of the total mass has been withdrawn. So they're asking for us to calculate what is the heat interaction by the time 1/2 of the total mass has been withdrawn. That means the first state has a mass of m1, right? And half of it is gonna be withdrawn, which is the half of it will remain at the second state. It also means that half of it is what is exiting the system. So that is also your exit mass. Okay, so your exit mass is half of the initial mass. Let me delete this. Okay, so the first thing is we sketched our system. We wrote down what is given, and looking at what is being asked is the heat interaction. And only way to find an energy interaction is actually to write the energy balance. And that is what we need to do. And first of all, to be able to write an energy balance, we need to identify what type of a system we are dealing with. Since with time, the mass inside the system is changing, this is an unsteady flow device, because as the mass is exiting, the mass inside the system is lowering down. So that means that mass is changing with time. That means we are dealing with an unsteady flow device, because with time the mass is changing. Okay, so once we identify that, now we can write down the energy balance on an unsteady flow device. We always, in all cases, start with the general form of the energy balance. Energy getting in minus the energy getting out is equal to the change in the energy of that system. Remember what the energy balance is. Energy balance writes down energy interactions on the left hand side, the energy transfer that is taking place, which is causing a change in the energy of that system. This right hand side lists the properties of that system. So this is the general form, but we can write more explicit form for this energy balance, and it is gonna depend on the system we are dealing with. So we now look at what type of energies are actually getting in, right? And we notice that the only energy that is getting in is heat. There is no mass, there is no work interactions in this problem. So only energy that is getting in is actually heat. Now we will subtract what energies that are getting out. We don't identify any heat, any heat or work getting out. So the only energy that is getting out is energy carried with the mass. And remember, energy getting out with the mass is related to its enthalpy if we assume potential and kinetic energy changes is 0. Okay, so therefore exiting energy is exiting mass, and its enthalpy is equal to, now the energy of that system at the second state, the internal energy is M2U2. We put a bar to signify that it is actually a specific internal energy, M1U1. Now let's solve this for the heat interaction, and let's figure out how we can solve that equation. Okay, so let's go to the next page and solve this for the heat interaction. Okay, looking at this equation, we are trying to find this term on the left hand side, and the right hand side. What do we know? We don't know this, we don't know this, we don't know this, we don't know the enthalpies, internal energies. So looks like we need to do some work, right? So let's start with the mass. How can we figure out the mass at the first state? We are given the volume, and if we in fact find the specific volume at the first state, I can able to calculate the mass at the first state of that system. Can I figure out the specific volume at the first state? Yes, if I have been given enough information. In fact, we are said that this is a saturated liquid, and also we are said that this is at 200 degrees Celsius. So at first state of that system, let's look at for what is the specific volume. It should be equal to the specific volume of the saturated liquid at that temperature. So let's read it from saturation tables. When we go to tables, table A4, saturated water temperature table, we know our temperature is 200. So our specific volume of the saturated liquid should be 0.001157 meter cube per kilogram, right? So that is the correct column. And let's, after we read that information, let's write it down. Zero point zero zero one 157. Okay, so if we know this, now we can calculate the mass. Because the volume is given to us, we are careful with the units. All the units should be matching to each other. This is also meter cube per kilogram. The result should be kilogram, and it should be 259.4. Okay, since I know the first mass, I know the second mass automatically because the question statement says half of it was withdrawn. So we need to find the half of this. Okay, very good. Now, can we write the mass balance on this system? And yes, we can, because unsteady flow device, actually the first thing you need to write down is the mass balance and then the energy balance. Let's see, we know now that for sure what is the second mass, what is the first mass. We actually can figure out what is the exit mass because half of it is also withdrawn. So that is the same as the second state mass. But this relationship can also be understood from the mass balance, okay? If you are writing mass balance, if you need to write mass balance for an unsteady flow device, mass balance looks like this. What is getting in to the unsteady flow device minus what is getting out as mass should cause the change in the mass of your system. This is the system mass. These are the mass interactions, right? In this case, what does it tell us? If we look at it, there is no mass getting in, right? That is 0. So the exit mass is then m1 minus m2. We just rearrange this equation because there was a negative sign. It became that exit mass is equal to actually m1 minus m2. You can also say this, right? Minus. So that is gonna give you the same thing, which is 129.7 kilogram. So if you are not immediately able to see the mass interactions and the volumes, you cannot identify it in your mind, you can just write down the mass balance, and from there you can actually see that since half of it is exiting, that half of it is actually remained, right, from the comparing to the initial mass. So now we have the volumes for all of those masses. Let me see if there is actually another color for this, right? So we have identified this. Now let's see if we can figure out internal energies and exit enthalpy. Well, we have already known the first state conditions. It is a saturated liquid water and it is at 200 degrees Celsius. We should be able to identify what the specific internal energy is because it is the specific internal energy of that saturated liquid at that temperature. Again, we go to our tables. At that temperature now we are looking at this column and we go down. Here is the specific internal energy of that saturated liquid. Okay, we can write it down. Now, the next thing is actually to figure out the second state internal energy. And how can we do that? Okay, let's think about it. What do we know about the second state? We know that second state has the same temperature. We are given the temperature. It's 200 degrees Celsius. What else we are given? Actually, we are not given directly any information that would help us to look at tables to figure out the specific internal energy. Because remember, to be able to read properties from a table, thermodynamic table, we need two intensive property. Here we are not directly told, but we are actually given another property, because besides knowing the temperature, we are also given the overall volume, and we have also calculated the mass. So what we can calculate is the specific volume at the second state. So we can actually calculate this because it is mass over volume, right? We have calculated the mass. Okay, this is wrong. To figure out the specific volume at the second state, we need to divide the volume to the mass. Okay, so 0.3. Okay, so now we know temperature, and we also know specific volume. Now we should be able to read what is the internal energy at the second state. But the first thing we do is always look at the saturation tables. At 200 degrees Celsius, what is Vf and what is Vg? And we need to compare our volume with that. So let's go at 200. This is Vf, this is Vg. And it looks like our number, our volume, is a volume in between. So our specific volume is actually bigger than Vf and smaller than Vg. And this tells us we actually have a mixture. To be able to calculate what is the second state internal energy, actually we need to use an equation that includes the quality, okay? And that equation is this. Because once you have a mixture, the only way to figure out your internal energy or any other specific property is to actually calculate it yourself through quality. Now, yes, we can figure it out, but we don't know what the quality is. So the first thing we need to do is figure out what is the quality at the second state. And to be able to do that, you need to use a known specific property at the second state, which is already given to us as the specific volume. So we're gonna go and calculate quality at the second state, right? And we're gonna use specific volume for that. The equation is so second state specific volume is what we have calculated for our system. Vf is what we have read for 200 degrees Celsius for saturated liquid specific volume. VFG is what we obtain from VG minus VF. Okay, we have found quality, and we can check the number if it has to be between 1 and 0, and in fact it is. So the probability of this being correct is high. So we just gonna keep this, and now we are given the quality. We can able to calculate what is the internal energy at the second state. We again read UF, the saturated liquid specific volume at 200 degrees Celsius from the same table, the same way we did. And that is 850.49. That was what we read. And we put quality times UFG. And we read and calculate 866.4946 kilojoule per kilogram. Okay, so we did that. Now let's take a look at what is left. Okay, so let's put another color here, green. And we know this, we know that, we know this. Now we know this, we know that. The only term remained, exit enthalpy. Okay. To figure out exit enthalpy, you need to understand one thing. What is the state of that mass that is exiting in our system? So the system is at state 1. And when the mass is exiting from that state, it is also at state 1, okay? So the exit state is actually equal to the first state of that system. Because from the first state, the mass is exiting at the same conditions, you go to another state, state 2. But the exit state has to be the same as the initial state of that system. So therefore, what you know about exiting water is it has to be at 200 degrees Celsius, just like the first state. And it has to be a saturated liquid, because that is what is we have at the first state, and that is therefore what is exiting our system. So for the exit state, we know we have 200 degrees Celsius and it is a saturated liquid. For that, we can read the enthalpy of that exiting water from the exact same table. Okay, so right now what we do is go to here and figure this out, go down. Let's see. Okay, you guys can see this is the exit enthalpy. Now we have figured out every term in our energy balance. What is left is all we have to do is plug that information in and calculate the heat interaction. Okay. Okay, what was it? M2U2 wait a second. M2 U2, right? M2 we have figured out. Okay. U2 we calculated using quality because it was a mixture, plus, okay, minus M1 U1. M1 is this. M1 is, U1 is from the saturated water tables. We figured this out. Now we need to sum the exiting energy due to mass. We know its mass is half of the original mass times exit enthalpy. We figure it out from the tables. And the conclusion should be 2308 kilojoule. All right, if you have any questions, you can write down to below this video. I will try my best to give you guys the best answer that I can.